chairperson of the 2018-2019 session. He's a retired physics lecturer from here at the University of Portsmouth. I'd like to thank Peter, where Peter is at the front there, for being a really good chairperson last year and for doing a really great job. He will be our vice chairperson descending this year. I'd like to thank Fiona for doing such a sterling job over so many years as vice chair, chairperson and descending vice chair. And I'd like to thank David Nixon for organising the finance system this year, and Ruth then for organising all the talks, which if you've looked at your piece of paper, we'll show you all the excellent talks we've got this year. For those of you with hearing aids, we do have a T-loop enabled this year. Okay, so I'd like to introduce, if you're ready, I'd like to introduce this, our first speaker for this year, which is Professor Chris Lintott from the University of Oxford. And his talk is called I Want to Believe, the Astronomer's View of Aliens. Chris Lintott is the Professor of Astrophysics at the University of Oxford, and he's a fellow of New College there. He's the principal investigator of Zooniverse. If you haven't seen Zooniverse, it's a great project. It's a big crowd-funded citizen science, that's the word, not crowdfunding. Crowdfunding differently. Citizen science projects. If you go on the internet and type in Zooniverse, there are tons of projects which you can get involved with, everything from arts to humanities to space science. He's also known as the presenter of Sky at Night, and I guess I should pass you over to him.
Thank you very much, and good evening. Blimey, that didn't happen during the sound check. That's not working at all, is it?
No, it's working.
Yeah. Maybe my voice has gone wrong, I suppose. What's happened? Why don't we just abandon it? That probably makes more sense. No? Okay. Well, I think how's that? That's still not great, is it?
Yes, microphones.
Let's just abandon it, otherwise we're going to spend the whole evening. Tonight's lecture will be about how we communicate. I think I just have to background the old-fashioned way. Okay. Sorry, that's just not working. Okay. I break all technology by looking at it. This is not anything to do with the locals. This is my slightly strange, unphysical effect on everything.
It was. There you go.
It was working 5 minutes ago. Good. Can you hear me at the back?
Yeah.
If I go quiet, which
The
is
other was
unlikely,
better.
please.
The other was much better.
Sorry?
It was better.
It's much better when you had it by your mouth.
You'd much rather I use this?
Yeah.
You need a referendum.
Yeah.
What do you want me to... Okay, I'll turn the volume up. How's that? Let me guess, that breaks when I go over here. Right, okay, I will stand still. This will be unusual. In fact, almost unique. Now, how's that? Good. No? Yes? Everyone happy with that? Yeah. Good. Given the part that talks about how to get a decision out of a crowd, I kind of feel like all of this is staged with communication with crowds. Anyway, it's lovely to be here. I love coming down to the University of Portsmouth, where I work with lots of the locals, so it's great to have an excuse. It's great to see so many of you coming out on such a beautiful late autumn evening. I feel particularly guilty that you're here, because this is not going to be a very good talk. Sometimes I give good talks, regardless of technical problems, but mostly they're about other people's thoughts and work. I think as science communicators, it's very easy to give good talks about things that other people are doing. For example, we know that there's an announcement on Monday evening of what the European Southern Observatory described as a new type of transient event in the sky, which I suspect, I have no idea, but I suspect is a new optical detection of a source of gravitational waves which if you've been following the story of LIGO and gravitational wave detectors over the last few years, you'll understand is immediately exciting. I was just sitting and playing with my phone before coming on, thinking about what I might say to you, and just discovered the dwarf planet Haumea out in the outer solar system. One of the things that helped denote Pluto has just been announced to have a ring around it, which we didn't know, and which we can't really explain. The outer Kuiper belt isn't really dense enough to make that kind of thing common, and so that's unusual and interesting. So you see, by talking about other people's stuff, I can interest you, but I don't want to do that tonight. I want to talk, I'm really trying to work out what I think about the kind of question that I get all the time when I tell people I'm an astronomer. There's sort of two sets of reactions when you say you're an astronomer to somebody. There's obviously the first one, which is, why are you talking to me? But if we assume we've got over that, people either say, you must be really clever, which is kind of gratifying, but also, you know, those of you in the audience who are physicists can experience this for yourselves, just pretend to be astronomers. But really, it's the outcome of 400 years of bad science communication. We're not clever. We're confused by the universe, but we are interested in it. And then the other kind of question is, have you found aliens? Also in this category are, did the Big Bang really happen? And how's it all going to end? But let's just deal with one of them tonight. So let's talk about the search for alien life, because I think it's a really interesting time. And I've titled the lecture, I Want to Believe, because I really mean that. I've discovered as I've thought about this topic, and I've participated in scientific attempts to answer the question of whether there's life or whether there's intelligent life out in the cosmos. I've realized that I really want there to be intelligent life out there. Bacteria would be fine, but really I want some people to talk to. And more than that, I want the galaxy to be teeming with spacecraft, with civilizations doing the kind of things we see in science fiction, because I think if that sort of thing is easy, that sort of thing is possible, if we're ever going to get to go out amongst the stars, and we or our descendants are going to explore the galaxy, then it seems obvious to me that we're unlikely to be the first to do that. I do not believe, the same way that I don't believe astronomers are uniquely intelligent, I don't believe, looking at the evidence around me, that the human race is particularly intelligent or capable. There's lots of evidence to the contrary. You know, we can build good things occasionally. And so I want a future for humanity that is adventuring and starfaring and not smouldering or short or other adjectives. And so therefore I think we want to believe that there are aliens travelling amongst the stars, and indeed that their presence should be obvious. And this is a thought I've had for a long while. And I remember standing on the beach, actually just south of Chichester, so not far from here, in Selsey, and seeing a bright light in the night sky. Brighter than almost anything else. Maybe as bright as Venus is when it's very close to the Earth and it's at its most brilliant. But this wasn't behaving like a planet. This light moved. It sort of drifted one way, and then every so often, and as far as I can tell, at a completely random pattern, it would reverse direction and zig and zag across the sky, for all the world like it was under the control of some intelligent agent. It wasn't an aeroplane. I'm used to seeing aeroplanes. It's not a satellite. They move slowly. It's not a meteor. They move fast and burn up. And I remember the feeling that I was dealing for the first time in my career as an amateur and then a professional astronomer with a proper UFO that I couldn't identify in the sky. Turned out to be a Chinese lantern, one of those things. I particularly enjoyed, by the way, the look on the faces of the people who thought I was about to ruin my reputation. I should have had a picture with alien on their side. But my point is that as an astronomer, I'm capable of recognising the unexpected in the night sky. And if there were spacecraft moving all over the place, then we should have been able to find them amongst the stars. We keep an eye out for things that change, that even very faint changes in the night sky. We don't have an overwhelming evidence for alien civilizations. So if I want to believe in aliens, I need to consider that evidence and find a way to argue that we're special.
Can you turn the light down a bit?
I haven't yet got to the slides, but yes, this is I see that you lot like your comforts, but yeah, we can turn the lights down. Anyone got any other request? I can do the thing in French. I've got the 4-hour version as well. Excuse me, mocking mostly myself. But it is nice to look at the night sky. And when we think about these questions, I think, look at this picture. You should look at this picture differently than you might have done 10 years ago. Because we now know something different about a view like this. We now know that every one of those stars is likely to have planets around it. The vast majority of stars in our galaxy, we now know, have planetary systems around them, have solar systems which might be homes for life. We don't know that because we've been able to image lots of planets. I don't have a gallery of images of nearby planets to show you. Instead, we have a wide range of indirect evidence that those planets exist. The problem isn't that the planets are too faint to image. If they're on their own and at the brightness that they are, we'd see them. But the problem is the stars are too bright. And the planets are about 1,000 times fainter than their parent stars. They shine only by reflected light, just as the planets in our sky do. And so it's very, very difficult to pick them out. It's like literally like trying to see a glowworm in front of a football stadium's floodlights. That's a very difficult problem of contrast imaging. So instead we look for indirect methods. Here's one of them. This, of course, is the sun, as viewed on a slightly foggy morning in Oxford. But this dot here is the planet Mercury, which happens to transit in front of the sun every so often as seen from Earth. Venus, of course, does that too. Here's a video of the last time that that happened. And on the left there, you can see there's Venus make its way across the face of the sun. And on the right is your sort of first-year laboratory, undergrad physics laboratory view of this exciting event. Never mind the picture, let's make it right. Those of you in the back will experience this shortly if you haven't already. And what you see here is this is just the brightness of the sun over time. And you see there's this dip. And if all we had was the graph, we'd be able to infer the presence of Venus just from looking at the brightness. It's a dip of about 1/10 of 1%. But that's enough to be detected, and you can infer the presence of Venus. And maybe you can even work out things like its size, based on how quickly the sun's light goes from at its maximum to the bottom of the dip. And so that's what we do. The game is to look at stars in the sky and look for repeated patterns of blinks that indicate the presence of planets. In particular, there's one space mission, a space telescope called Kepler, that looked at one patch of sky containing about 1.5 million stars that were accessible to this small telescope. And Kepler reported the brightness of about 150,000 of them every 29 minutes for 3 years. And people have gone through that data and looked for these repeated patterns of blinks. Now, Kepler will have missed most of the planets that exist around those stars. You can think about that intuitively. If you have a star and the planet happens to orbit like this, from your point of view, you'll never see a transit. So you need it to be just right. But you can take out for that in the statistics. And the result of Kepler's mission has been an explosion in the number of known planets. This is now more than a year out of date, so you can have a few thousand. But these big jumps in the number of planets around other stars, exoplanets that we know, are the responsibility of Kepler. And that's meant that we've been able to do statistics, so we can start to ask questions about what the most common planets in the galaxy are. So this is the known planets, the known transiting planets by size. And so we've got super Jupiters, things that are very large Jupiter-sized planets. We've found a few of those. Some a bit smaller than Jupiter. We've got lots of Neptunes. Over here we've got Mars and Earth-sized planets. And then the categories in between, the sub-Neptunes, and the much more exciting super-Earths. Sounds much better than puny Neptune. But the most common type of planet in the galaxy isn't anything we have in our solar system. It's a planet of a size between Earth and Uranus and Neptune. we can ask statistical questions of the planet population. And one of the questions you might ask, if you're interested in aliens, is how many of these worlds are suitable for life? And I should say that most of this talk, I think I'm going to follow convention and talk really about trying to find our kind of life. By which I mean life that's probably carbon-based, which uses water and needs liquid water to survive. Now we can have an argument later about whether that's a sensible assumption, but I think you have to put some limits on what you think life might be to have this discussion sensible. I would love there to be, as Carl Sagan talked about, giant jellyfish swimming amongst the clouds of Jupiter, living on ammonia and enjoying a hydrogen-based lifestyle. But I think if you include them in your scientific calculations, then you have to include everything else as well. So maybe the universe will surprise us, but for now let's talk about boring old carbon, liquid water, fueled life. And I can justify that a bit if you want to ask about it later. And so that means I need to find a planet like ours to be a home for life. The gas giants are no good. Probably everything from here on over, and many of these super-Earths, are not rocky or icy worlds. These are gaseous worlds, so we can rule them out. But we still know of a good few hundred rocky planets that are likely to be rocky. And because the odds of any given planet transiting, getting in front of its star as seen from Earth, are low, we can extrapolate that up to deduce that rocky worlds the size of Earth, are common in the galaxy. A good estimate is that there might be something like 200 million such worlds in the galaxy, at least. So there are lots of homes for life out there. So 20 years ago, I think I could have got out of my dilemma, my explanation for why there are no starships seen obviously scooting between the stars would have just been the planets around. That we're lucky to be in a solar system that has at least one and maybe a couple of rocky bodies that maybe once had life. But that's not true. We now know that planets are common. Should be careful about these comparisons though. Size, famously, is not everything. And here is another view of the same day. I figure this is the Portsmouth District Physical Society, so I get to show graphs in a public lecture. Less picky audiences would be upset and would rather see some pictures, but I can see that you like graphs. So these are all the discoveries. The colours are just different data sets. But this is from Kepler. And the small dots show the planets, the estimated radius of the planet. So Jupiter's up here, Neptune's in here, Earth's down here. And then this is the period in days. So most of these are pretty close to their star. They whiz round in only a few days. And that makes sense, because after all, you build up confidence that these planets exist every time you have a transit. And so you need lots of transits to gain confidence that this planet exists. But the big dots, this is Mercury, Venus, Earth, and Mars down here, very roughly placed. And you can see that they live in a desert. And so we can argue, perhaps, that we haven't found any planets like our Earth. We found larger planets that go around very slowly, and we found small planets that whiz around their stars very quickly. But these are very un-Earth-like places. And that, I think, is okay. I think that's just a coincidence. As I just said, these are hard to find. Small planets that orbit slowly produce small blinks that are lost in the noise. And so my prediction is, I'm very confident that as we get better telescopes, as we do a better job of this, there are new European and American space missions, there are people doing this from the ground, as I'll say in a second, this space will get filled in. Some of the other planets will remain weird. Look up here, you've got Jupiter-sized planets that are only a day or two, that have years that are only a day or two, very close to their parent star, which leads to things like this. This is HD, this is an artist's impression of HD 209458b. I love the names of these things, they're so poetic and interesting. This is a Jupiter-sized planet that's only 4 million miles from its star. And you could argue that this is the largest comet that we know of, because we've detected traces of its atmosphere boiling away. And in 1 billion years' time, this planet will have evaporated entirely. This is, again, not like anything we have in our solar system. These solar systems, although we have planets, although we have rocky planets, and although we may end up with rocky planets in orbits like the Earth's, these planets are not like our solar system. But actually, this is the wrong graph to plot. I know, which is depressing. Because the physical thing we care about is probably not period. I think I'm going to play science fiction author for a second. Imagine what would happen to the Earth if we increased the length of the year by 25%. Really terrible superhero or supervillain threat. You know, it could be $1 million or increase the length of the year by 25%, or you have to wait slightly longer between Christmases. University term is slightly longer, so you get to learn more physics, which is exciting. You know, the effects are small. What you care about is the fact that to increase the period, you have to move the planet outwards. And so the temperature drops. The physical axis we should plot here is temperature. And so here is a selection of newly discovered planets with the temperature. So this is actually the energy received by the planet as a function of Earth. So 1 is Earth's and the energy the Earth receives from the sun, and the temperature of the star. This green belt here is an attempt to think about what's called the habitable zone. It used to be called the Goldilocks zone, the region that's not too hot and not too cold. But then exoplanet scientists got serious and got upset with having trivial names like Goldilocks. And so this is the region in which you can have a rocky planet like the Earth, and in which, if you do, and you have an Earth-like atmosphere, then you will have conditions on the surface where liquid water can exist. And so if we want to find homes for our type of life, these are the planets that you should be looking at. And Kepler's found lots of them. My favourites, actually Kepler's found lots of them. These are the Kepler planets. You can see there are plenty there. Most of them are around smaller stars. It's easier to see planets around fainter stars. And so we're finding more and more around red dwarf stars. But we found some around sun-like stars as well. So we have this set of habitable zone planets. So they're not common. There are probably 8 good candidates out of the 4,000 that Kepler have found, but they're there, and that probably means that they're common. And in other cases, we found systems nearer home that are just as good. There are other ways of looking for planets. Instead of waiting for blinks, if you care about a particular star, you can stare at it with a large telescope and measure its spectrum. And with its spectrum, you can look for a Doppler shift that indicates movement. And if you do that, you'll find that around some stars, they're doing a strange wobble. They come towards us and away from us. Not particularly fast, maybe a meter per second, sort of walking pace. But if you can build an instrument that can measure the movement of a star to sort of walking pace accuracy, then you can detect the pull of a planet going around that star. So just as the planet's gravity pulls, just as the star's gravity pulls on a planet and keeps it in its orbit, a planet's gravity will pull on the star. They both orbit their common centre of mass. Fun bonus fact for the evening, by the way, the centre of mass of the solar system is just outside the sun. It's about 1,000 kilometres above the solar surface, which is probably coincidence. But Jupiter's large enough to disrupt it. So the star will wobble. And if you watch the wobble, you can deduce the planet's existence. Sometimes you see complex wobbles. And that's been done in particular by a group of Belgians who built a telescope called TRAPPIST. TRAPPIST named after the beer, though it's also an acronym. And so TRAPPIST is a 7-planet system. TRAPPIST-1 is a 7-planet system. So there's B, C, D, E, F, G, and H. Again, the poetry of the names is wonderful. And we've had great fun with TRAPPIST because several of these are in the habitable zone. And they're all very packed closely together. The star emits only about 1/100th of the energy that the sun does. And so these planets are very close, and yet they're in the habitable zone. And so NASA have even gone as far as producing posters advertising trips to these places. So here's your tourist poster for TRAPPIST-1e. And you can see this is the actual projected size of the nearby planets in the atmosphere. Although there's something strange going on with the lighting. And I'm not too sure about the 70s vibe, but you know. This is a nearby system that has habitable planets. And in fact, it's close enough and the star's faint enough that we have hopes that the telescopes we're building now will let us study the atmospheres of these planets. You want to do that because you want to be able to see whether there are any signs of life in the atmosphere. You need a big telescope. This is the European Extremely Large Telescope, the ELT, which is the next generation telescope after the Very Large Telescope, which we have today. The running theme is that astronomers shouldn't be allowed to name anything. And it started off actually as the Overwhelmingly Large Telescope, which had a mirror 100 meters across, but it turned out that that was indeed overwhelming. So the ELT, the European Extremely Large Telescope, will have a mirror probably 32 meters across, made of segments, and that's Big Ben for scale. I've been struggling to get my head around how big this thing is. This is a truck, and these are astronomers for scale. But it's something hit home to me. I was talking to some of the people responsible for this project. Construction is now underway, and they've just signed the contract for the dome, for the enclosure which this telescope is going to sit in. And I asked them who bids, what kind of company wants to build an enclosure for a telescope where the mirror is 32 meters across. And the answer is it's companies that normally build very large international sports stadiums, because that's the scale of this. It's like dropping a telescope into Cardiff, into the Millennium Stadium in Cardiff or something like that. So the ELT will let us look at the atmospheres of some of the nearest habitable planets. And what you'd be looking for many things, but one of the things you might look for is oxygen. Because on Earth, oxygen is generated by life. And if all life on Earth was to die out right now, well, it would cut the lecture short, for starters. But the other effect would be that very quickly, all that oxygen would be bound up in rocks, quickly drop out of the atmosphere over the course of 1 million years or so. And so if you saw a strong oxygen signature in the atmosphere of a nearby planet that you knew was about Earth's size, and which you knew was in the habitable zone, I think you'd have a strong circumstantial case for there being life on that planet. And that's a headline you might read in the next decade. We're building the tools for us to do that. And we found planets that we look at. TRAPPIST-1 will almost certainly be one of the first stars studied with this beautiful new instrument. So that's really exciting if you like bacteria. And you know, bacteria are fine. You know, but we're physicists, so I want something a bit more exciting than that. And while it would be a great discovery, it would be an unbelievably exciting discovery to know that there was life on a nearby world, it doesn't solve my starship problem. It doesn't get me flying amongst the stars that I've seen on television, which is the goal of all of this. It doesn't help me understand the future of humanity as a spacefaring race. So let's go back to statistics for a second. I said that there were lots and lots of rocky planets. But if you do the statistics, and you insist not only on a rocky planet, but a rocky planet in the habitable zone around the star, you get numbers that are headline makers. This is from the Smithsonian magazine. This is a study that suggested there were 17 billion. This is an average rather than conservative estimate. There's 17 billion Earth-like planets. That's rocky with the right temperature for liquid water to exist. And I like the headline on this because it says you can't throw a rock in the Milky Way without hitting an Earth-like planet. If you don't believe that, you can go outside, try it, find it's true. See, normally that joke doesn't get a laugh. It's mostly there for my amusement. But you're clearly an audience of a higher stripe. You understand these things, or are willing to tolerate it. It's not clear which. And so these things are common, and actually it's even better than that. And an illustration of how easy it is to find planets was brought home to me a few years ago. So my own research is mostly galaxies. I care about how galaxies form, and I can tell you about that some other time. But we do that, as you heard in the introduction, by invoking citizen science. Actually, it's something we do with the team here at the University of Portsmouth. But we ask the public for help, initially in classifying galaxies, but increasingly in a whole variety of scientific endeavours where there's so much data that professionals can't be expected to look at it all. And one of the most ridiculous and fun projects we've run is a project called Planet Hunters, which asks people to help sort through data from Kepler to look for planets. And you lot will love this. This is an example Planet Hunters data set. And when this launched, I thought no one in the world would look at this for fun. This is a graph. Honestly, Science Communication 101 is don't show people graphs. I've broken it already, but we've discussed that because you're great. But this is data for one star from Kepler for 30 days. And what we're looking for here is a blink. And the task is to look for repeated blinks. And this is a stupid thing to ask people to look for. For starters, we're looking for a repeated pattern in noisy data. There are textbooks on how to do that automatically. You could do simple things like take a fast Fourier transform, or more complicated things. You can find repeated signals, but the data is noisy. The camera's operating right on the limit of its sensitivity. These stars are faint. They vary, they have star spots, they oscillate. The camera occasionally drops out, different pixels respond slightly differently to the environment of space. And so you have this noisy data, and we decided it was worth asking people to look, just to make sure that we weren't missing any planets. So you can see here there's a dip. This is actually a Neptune-sized planet, highlighted in, this is the result of the Planet Hunters. So the volunteers found this one. We found a repeated series of dips and found this world we call Planet Hunters 2b, lovely name. PH2b I like for a couple of reasons. So one is that one of the discoverers was a guy called Roy Jackson, a 71-year-old retired police inspector in Gateshead. So we've gone from discovering an exoplanet 20 years ago, being something you might win a Nobel Prize for, to now being something you can do at home on your computer, which is very exciting. Secondly, Roy gave an interview on local television when he made this discovery, which was lovely. And the first question they asked was, Roy, what made you want to discover a planet? And he stared straight down the lens of the camera, and he said, well, there's only so much gardening you can do. And there was nothing to it. And I love that. You can sort of not only can you discover a planet from your computer, you can discover a planet from your computer by accident, because it was raining a little bit, or you finished pruning the roses. So I think that's fabulous. Same thing I like about PH2b is that it's a Neptune-sized world, so it's not rocky, but it exists in the habitable zone. It's in this Goldilocks zone, where if it was rocky, it might have the right temperature for liquid water. And we wanted to get some publicity, and so we started thinking about what it would be like to be there, and talking about life. And we realized that it seems plausible that PH2b might have moons. And if they have moons, our gas giant planets all have moons. Some of them are large. Titan, Saturn's largest moon, has an atmosphere. Enceladus, the moon of Saturn, has a liquid ocean, so do two of the moons of Jupiter. Triton, Neptune's largest moon, has all sorts of strange things, cryovolcanism and other stuff going on. So if you had a large Earth-sized moon around PH2b, then that would be an ideal place for life. This is an artist's impression of what it would look like to watch your planet rise over your Earth-sized moon, which is the perfect habitat for life. So I should include not just the 17 billion Earth-like planets, but also some multiple of the large planets that we found in the habitable zone as well. So even if each of those has one Earth-like moon, Earth-sized moon, then we can multiply by 10 the number of habitats that exist. And so the places at which life and intelligent life could exist are almost uncountable. I mean, we're counting them, but there are lots of them, is what I mean. And so we cannot explain the lack of really obvious starships by saying that there aren't enough habitats out there. And so people have gone looking for aliens. This is an image of the Parkes radio dish in Australia, currently one of, currently undergoing the world's most sensitive search for signals for what's called SETI, the Search for Extraterrestrial Intelligence. SETI has been ongoing for a mix of telescopes for more than 40 years now, and has found nothing convincing. is currently being very well funded by a Russian billionaire who likes the idea. So 20% of the time on parks and until the hurricane hit at Arecibo, the most powerful radio telescopes in the world, was being dedicated to looking for the kind of signal that would be hard to explain by any other means other than intelligence. The game is usually to look for things that are unexpected. For example, pulses at very narrow ranges of frequency, or which repeat very quickly, with the idea being if you find them, you've either discovered new astrophysics, or you found a signal from an alien civilization. But there hasn't been much success. And it's not clear, to me at least, whether we should find that depressing or not. I should say that I think the SETI is definitely worth doing. I think it's worth a small investment because it may pay off dramatically, and it would be a shame if there was a message and we weren't looking for it. But there are plenty of suggestions as to why it might fail. For example, our radio telescopes are still relatively new. We're building an amazing new one, the Square Kilometre Array, which will use dishes spread across southern Africa and Western Australia. And SKA, if you believe the optimists, will detect signals the strength of airport radar on planets around any of the nearest couple of thousand stars. And that's really impressive, but that's a tiny proportion of our galaxy, which contains 100 billion stars. And so by listening, we're only really listening for either deliberate signals aimed at us, or we're listening for very nearby accidental signals. So we don't have the capability to do a proper scientific research on a large range of galaxies. Plus, you can argue that radio is yesterday's technology. When SETI got started, it seemed obvious that advanced civilizations would be loud in the radio. But over the last 20 to 25 years, the Earth has gone from being quite radio noisy to radio quiet. Instead of doing long-distance communication by broadcasting in a broad fashion to the upper atmosphere, we now target microwaves to satellites, where the number of broadcasts that actually head out into the atmosphere are much fewer. And it may be that you only have a tiny period at which a civilization uses this sort of broadband radio technology to communicate. You do SETI in other ways as well. This is Veritas. It's a gamma ray telescope. Normally looks for flashes of light in the Earth's atmosphere caused by high-energy particles entering the atmosphere. But they've done what's called optical SETI. So they look for transients. They look for very high-frequency pulses of light, maybe because of aliens communicating via lasers, for example. And they've found nothing too. But really what one should do is keep an open mind and consider anything unusual that one finds in the cosmos to see whether it might be plausible evidence for the kind of alien life that I'm looking at. And I've always believed that in theory. I've always admired people who do that. There's a guy called Duncan Forgan, for example, who's at the University of Edinburgh, who has a very nice rhythm to his publications. He writes 3 sensible papers, cosmologist. So they're not that sensible, but mainstream. And then he writes a paper about a test for alien existence. And then he writes 2 more sensible papers. So my favourite of Duncan's, for example, is that he hypothesised that if you had aliens that existed in a young star system, they would see that there are abundant asteroids around them, and they'd go and mine them for natural resources. The people on Earth are starting to think about doing this with our asteroids, so they're economically it's a bit problematic. But let's assume that that's true. Duncan then reasoned that mining, whatever technique they use, if they're using, I don't know, the hypergalactic blast arrays or whatever it is, or teleport, mining produces dust. And by looking at the spectrum of dust around these stars, you can get an average particle size. And so he said, okay, if aliens have been mining, we should see an increase in small dust particles and a decrease in the larger things. And so he went and tested all the observations we have. He didn't find anything, but that's the kind of creative approach to alien hunting I think we need. And I'd always sort of admired this from a distance, and then I got caught up with it. And I got caught up with it because of a star that Planet Hunters volunteers pointed us to. This is the best graph of the night, by the way. It's so good, hidden bits in it to show you piece by piece. This is the light curve, so this is brightness over time for a star called KIC 8462852. Those keeping notes. And what you can see is just after Kepler started observing this star, there was a dip in brightness. Not by much. It's actually quite big for a planet, but this could be something like a Jupiter-sized planet getting in front of the star. But one dip is not enough to claim a planet. They could just be the star is maybe. So you wait a little while, and there's a second dip. So that's exciting. But you really need 3 dips, 3 regular dips to be able to even begin to talk about the discovery of a planet candidate. That's become the gold standard. And this star, as you can see, didn't dip a third time, or at least not in the same way. It basically did very little for about a year and a half. At which point, it lost 20% of its brightness for about 3 hours. And then it came back. And then it behaved as if nothing had happened. And stars don't do this. No other star out of the 150,000 stars that Kepler has studied has ever done this. And Planet Hunters volunteers found this dip, which was rejected by the automatic computer, which the algorithm said this was implausible, so didn't draw our attention to it. But the volunteers did. And they spotted this, and we kept an eye out as more data came in. And nothing happened for about another year and a half, and then this happened. The star, to use a technical term, went crazy for a couple of weeks. It faded, it brightened, it lost 20% of its light again, it came back, and that continued for a few weeks, and then the Kepler mission ended. If you want a scientifically informed conspiracy theory, what happened was Kepler relies on things called reaction wheels to point, and 2 of its 4 reaction wheels had broken by that point, so it couldn't stay pointing at one part of the sky. It's still doing interesting stuff, it's drifting around and it's looking at different parts of the sky, but it lost its ability to stare at this one field. So, how do we explain what's going on here? Well, one option's quite fun. One option, the first thing we thought of, was to look close to home. Imagine Saturn transiting in front of a star. Actually, this is how those rings around Haumea have been discovered. If an object with rings goes in front of a star, as seen from your location, you see a little blink because of the rings. Maybe in a pattern, if you have Saturn's rings have gaps, so you have a bizarre pattern of blinks. Then you see the star in this gap, and then you'd get a big dip, and then you'd repeat as you go out this way. And we've actually seen this happen. To give you an idea of how crazy the data is, this is a different extrasolar planet. And at the bottom here, what we're going to do is, at the bottom here, these yellow dots are measurements of the brightness of the star. You've got time in days running along the bottom, this bizarre unit that astronomers use. And then we've got a model that's going to go across the top, which is a ring system around the star. And the yellow star in the middle is the thing. So you start off at constant brightness, and then you disappear behind a ring, so you lose some brightness. And then the pattern of rings is arranged to explain the detail of this quite bizarre light curve. So you have to force this to fit, and you put your rings in exactly the right position to explain this light curve. But it works quite well, and then you disappear behind the planet, or behind whatever's in the centre of the disk, and then you come out the other way. But there's one constraint, which is really nice, which is that this has to be symmetrical. You need a symmetrical system of rings. There isn't any physics that would maintain this off-axis. And so that works really well, except that our thing isn't symmetrical. So that's not a good explanation. The next thing we thought about was sort of similar to the ring system. We see that lots of stars have dust disks around them. So this is the star Fomalhaut, except with the star, this is a bright star in the night sky, but with the star taken away. And so what you see here is the remaining light is scattered light from a disk of dust, of small particles that surround the star. And you can imagine a dust disk moving across the face of the star and blocking out the light. And that would work, except that dust glows brightly in the infrared. Light from the star is absorbed, and the dust re-radiates in the infrared. And this star, our star, KIC 8462852, isn't bright in the infrared. And so if you put a limit on the amount of dust that's there, you don't have enough dust to explain this. So it's not dust. And we ended up coming up with a model which suggested that what we had was a fleet of comets blocking the light from this star. So a large comet that breaks up, and then you have bits of comet arranged in their orbit, rather like this artist's impression shows. And you start off with a small bit of comet, then another one, then a larger bit about a year later, and then the main body, or what's left of it, later on. And that makes some sense. Comets do break up. But the trouble is, and we published a paper that said maybe this is the first discovery of an exocomet. The trouble is, when people who knew about comets came and looked at this, they told us that our comet would have had to be the size of this thing. This is the dwarf planet Ceres, the largest object in the asteroid belt, 1,000 times larger than any known comet. So, to explain our bizarre star, we need to say that we've discovered the largest comet known by a factor of 1,000, and that it happened to just break up just before we came along and saw it, and that this stuff happens rarely enough that we only see it around 1 of the 150,000 stars. And so you can believe those things if you want to, but I don't anymore, and most astronomers don't. And so people started putting forward other suggestions as to what this might be. And credit at this point goes to a guy called Jason Bright, who's at Penn State in the States, who published a paper suggesting that what was blocking the light from this star was an alien megastructure. This is a picture of an alien megastructure. The idea is that a very advanced civilization will need to construct solar panels, and you don't want to waste any light, so your solar panels will essentially envelop your star. This is often called a Dyson sphere, and if you construct a solid sphere, it collapses, or a Dyson swarm. And so Jason's idea was that they're in the process of doing this, and so every time a large alien solar panel gets in front of the star, it blocks out the light. It's a useful hypothesis. Well, it's an interesting hypothesis. I like the idea that a bunch of volunteers online on one of our projects will have discovered alien life. That's quite flattering. But it's difficult to know what to do with. How do we test this? Turns out you can do it, and you can work out, you have to make an assumption about the efficiency of alien solar panels. So there's some sort of theoretical limits on that, and you can work out the infrared signature of this thing. And it's allowed by the observations that we've got. But if we get more detailed infrared observations during one of those dips, we can rule this in or out. The other thing that happens is that if you use the word megastructure, alien megastructure, in a paper, the press get a hold of it. And the press very much enjoyed our alien megastructure. I particularly liked the Daily Mail, who criticised us for covering up the evidence in a paper that we published. But they also produced an amateur astronomer who said that he thought the whole thing was ridiculous and it was clearly comets going around the star, which is also fun. And so this thing still burbles around the internet. I don't have time to talk about what's happened since. One of the most intriguing things is that the star itself seems to be fading on a time scale of 100 years or so. We went and got historical observations. And so whatever else is going on, the star itself is misbehaving. And it's been the target of a study by a suite of robotic telescopes around the world. This is the one in Hawaii. And we just caught earlier this year, this is this summer's light curve, it's dipping again. And we've managed to get, by asking the astronomers of the world to help us, we now have observations with some of the largest telescopes in the world taken during these dips. And so I'm hopeful that within the next few months we'll have a good sense of what this thing might be and whether the alien megastructure hypothesis is still alive or not. So that's the closest I've ever got, never mind Chinese lanterns. You know, is this aliens? Probably not, but it's more like aliens than anything else I can think of right now. But it doesn't get me back to the fact that aliens should be obvious. I really want to see alien spaceships because then we can know that colonising the galaxy or exploring the galaxy would be easy. And so I'm left trying to argue, if I'm not prepared to say that we should have found them by now, I'm left trying to explain why we're special. Because if I want a star-faring future, And I can't argue that intelligent alien civilizations are common, because we would have seen them mining, we would have seen them building their solar panels, and so on. I'm left having to argue that we're not on a normal planet, that there's something special about where we are, because that allows us not to be special. The other option is to say that we're special, we're uniquely intelligent in the history of the universe, and therefore will overcome what destroyed all other civilizations. So, how might we be special? Well, Earth-like doesn't mean Earth-like. This is an artist's impression of Proxima b. There's a great kerfuffle about the fact that our nearest star now seems to have a planet going around it. It seems to have a planet going around it that might be in the habitable zone. And it was reported as an Earth-like planet. But it's close enough to this very small star that it's probably tidally locked to it, so it keeps the same face to its star, just as the moon keeps the same face locked to the Earth. And so that makes imagining an ecosystem rather uncomfortable. You do it probably. You can imagine living in the twilight zone and sort of perpetually running around the planet as it spins, as it orbits. That's difficult. And the star is also violent. So Proxima Centauri it has flares. It brightens suddenly. It's probably not a very nice place to live, this planet. And so I think you can knock the statistics down a bit by being more picky about where you want to live. Not enough that it's got to be rocky and have about the right temperature, but you probably want an atmosphere. You probably want the star to be stable. You probably want a sensible length of day. And, yes, water's good, but maybe we need land as well. And so on and so on. You can start, it's a bit like picking a holiday. You start off with a general sense that you'd like to be anywhere but here. And slowly narrow down to what you actually want until you get there and you start complaining that the room is slightly smaller than you expected. Maybe that's just me. And so that's true, but remember we started with 17 billion Earth-like planets, multiplied by the number of moons, or add the number of moons. I just don't think you can get yourself out of the statistical hole that way. Maybe we need something really unique. And look at the solar system. If you look back as an outsider, this is a beautiful picture of the Earth and the Moon, taken from a camera on a spacecraft in orbit around Mars, which I think is rather lovely. We look unusual. We're a double planet. There isn't another large planet in the solar system. Pluto has a claim. But there isn't another large planet in the solar system that looks like this. And so you can argue that the Moon is important. The Moon, for example, keeps the Earth's axis stable. Mars does not have a large moon, and so the tilt of Mars's axis wobbles over the course of several million years, which has a dramatic effect on the climate of that planet. It doesn't have a stable climate, whereas the Earth does because the Moon exists. You can make other lunar arguments as well. And so that's interesting. And so I think you could predict, if you were brave, that we won't find moons around exoplanets, and that what makes our place special is that the Moon exists. And that worked really well as a near conclusion to this until a couple of weeks ago, when it was accidentally announced that we might have found the first exomoon. So now this is difficult to do. Remember, we can't find planets directly. We have to wait for the blink that shows us that they're there. And if you remember, you could find an exomoon, a moon around an exoplanet, by looking for an extra transit. Like you imagine if the moon was following the planet, you get a blink, and then there'd be an extra blink as the moon also covered the disk. And the reverse as they went off. But the trouble is, next time that planet came round, the moon would be an arbitrary number of orbits round, and maybe it would be in front of the planet, so you see a perfectly normal transit. And then the next time round, maybe it'd be 60 degrees. And so you had this continually changing signature. But people have been looking, and a team led by David Kipping, who's a British astronomer working in New York, in Columbia, thinks they may have found a Neptune-sized moon around a Jupiter-sized world called Kepler 1625b, and the moon is Kepler 1625b1. I'm really glad we've got a great naming scheme for these. And so we may have to say, they're not sure. It's from the transits, they have a 3-sigma detection. So it looks plausible but not secure. And they've got Hubble Space Telescope time this week to to look at it and see if they can detect it properly. And what David and co didn't realise was that when you apply for Hubble Space Telescope time, your application is public. And so they were trying to keep this quiet, and then everyone saw online that they were looking at this star to look for an exoplanet. And so they announced it. But this is not like our moon. Okay, Jupiter, the large planets can have moons, that's nice. But our moon, we need a rocky planet with a large moon. So I still think it's a sensible prediction, based on the dearth of intelligent life out there, that our moon is special. I think you need probably about 20 years more data to prove me wrong. So I'm going to say that I'm going to claim that. I think that's a sensible answer to my dilemma. But beyond that, your only other option is to start blaming biologists. Maybe that's okay. I've assumed in everything I've said that it's easy for life to get started. And I think there's good reason to believe that. Life on Earth got started early. These are stromatolites, which existed in pretty much their current form 3 billion years ago. And there's good evidence that life existed on Earth almost as far back as 4 billion years ago. The Earth is only 4.5 billion years ago. So the fact that life got started quickly on Earth suggests to me that it was a likely event. If I sold you a lottery ticket and I didn't tell you anything about the odds of winning, and on your first go, your first ticket won, you'd be entitled to believe, I think, that I hadn't sold many lottery tickets. You wouldn't be sure. You could have just got very lucky, but the odds, that you'd be entitled to believe that it wasn't a hugely competitive lottery. And so I think that's how I think about life on Earth. Life got started quickly, therefore I think that life, even though we don't know the details of the origin of life, got started quickly wherever it got going in the universe. That is, incidentally, why Mars is important, because it's an independent test of that principle. But intelligence, our kind of tool-using, hopefully starfaring, gin-drinking intelligence is really rare. It's rare on Earth now. You know, for every person on Earth, there are 300,000 ants. Don't go and claim them, but that's the ratio between you and the ants. So, and God knows how many bacteria and so on. So, if you were trying to describe life on Earth from the perspective of an alien biologist, if you went by mass or by number, you wouldn't consider us. On the other hand, intelligence also took a long while to get going. The dinosaurs were in charge, in the sense of being the dominant land animals, for hundreds of millions of years, without feeling any need to try and build spacecraft, as far as we know. I didn't even make that assumption. And so, we may just be a freak. Maybe intelligence is real. Maybe the real explanation is that even in the state we find ourselves, we might well be the most intelligent species in the Milky Way. And I struggle. The reason this talk is a messy, random bunch of thoughts is that I struggle to believe that. I have no scientific reason to argue against it, but I find it actually slightly scary to look up at a night sky that has hundreds of billions of stars in it, where our galaxy is one of hundreds of billions in the universe, to know that there are all these worlds out there that we're capable of discovering, detecting, describing, arguing about, imagining, and to think that on all of them, even if there would be life that we're capable of detecting, telescopes we're building now, that we may be the universe's most aware and most intelligent species. And on a good day, I think that gives us a responsibility to try and find out as much as we can about this universe in which we find ourselves, with a self-aware bit of it. And if we're all there is, it would be an awful shame if we wasted our time, which might be brief, arguing with each other rather than trying to discover new things. And on a bad day, I just wish somebody would come down and sort it all out for us. Thank you very much. Thank you very much. I hope the sound was okay, never mind the words. I have time for some questions, I think. So, sure there's nothing controversial. I don't think I've said so. So where should we start? Let's start with you.
That's radioactivity is the drive of evolution. We monitored radioactivity elsewhere in the universe.
Good question. So the question, for those who couldn't hear all the way, was radioactivity seems to drive evolution. So do we understand anything about radioactivity elsewhere in the universe? I think in terms of sort of the radioactivity that you normally think about, from deposits of radioactive materials in rocks, the assumption is that the Earth is not special in that. But what I worry about, I think, or think about, is the influence of active stars. So the sun has violent outbursts, solar flares, and coronal mass ejections that send charged particles out into the solar system. And we're mostly protected from them by the Earth's magnetic field. But we don't really understand the details of how planets develop magnetic fields, so an unprotected planet would be a very awkward place for our kind of life. It's also true that other stars are more active than the Sun, and that they have more of this sort of activity. And so Proxima b, the planet around the nearest star, people have argued that even if the planet was perfectly nice, these flares are so common and so large, and the planet is so close, that it would be difficult to have stable, to have stable life there. We don't really know what our tolerance is there, but people are beginning to think about that. So thank you. Other questions? Yeah.
Yeah, I spent some time on the two universe websites. But I couldn't find much feedback as to whether what had been detected was real or not, so I think the location isn't ready there yet.
Yeah, no, thank you. So the questions about spending time on the universe and not getting feedback from what's been detected. So the problem is that it still takes quite a long time to do the science. So the teams are working through the data and are publishing what we can when we can. So Planet Hunters, there's a page, Universe.org/publications. So Planet Hunters has about 12 papers. There are about 100 confirmed or nearly confirmed planets. But everything's useful. And so it's a different talk really, but we work with the scientists on each project to make sure that they're using the data and make sure that it's not useful. So I'm sorry if the feedback's slow. Sometimes it takes a while for people to work through these things. Next question. Yeah, so.
I have a suggestion. Suppose, for instance, that we actually are one of the sleepiest people in the universe. As an engineer, and wanting to communicate with a star, one would need to point directly at it. And to do that, one would need to use unless our transmitter was of great size, one would need to use very small object. The wavelength associated with small objects is much higher frequency than we use here for radio waves. So I envisage some sort of communication system, interstellar communication system, which would involve sending tiny particles packed with information. After all, we do it all the time here.
Yeah.
Maybe they're going on all the time.
Yeah.
We may be like sort of fish on a television.
Yes.
Who can't visit radio waves.
Yeah.
We haven't generated. With us all receivers. The thing to do now is to generate a receiver.
Sure.
Which we look with magnetic collectors or something.
Yeah.
And slow down and maybe develop the.
I'm just going to interrupt you because I'm going to have to try and repeat all of this for everyone. So let me summarise your point and then let's have a detailed discussion about it. But I think the gentleman's making a very valid point, which is that we're making assumptions about what the communication system being used is. And if we make the humble assumption that we're mere beginners, that we're amongst the stupidest people in the universe, which I find reassuring, then we should be looking for other communication systems, maybe people are trading particles or directed beams or so on. And so we need to develop new techniques. And I think that's absolutely right. I think the problem is that one can imagine anything as a means of communication. And so what we should do, I think, is try and get as much information about the universe as possible, and look for particles as well as light, and then look for unusual things. So I think that's a really sensible strategy. Really, the other thing it hinges on, which you hinted at, is whether we're looking for a signal that's beamed to us, whether people are trying to communicate with us, or whether we're detecting the accidental signs of life. There's a great explanation for why we haven't seen aliens, which is that they're all much more advanced than us. But there's something called the national park hypothesis in play, which is that for some reason, some ethical reason, they feel it's important that we get to develop as a civilization without being influenced. And so they're hiding. If you go 5 light years away, there's a sign that says, please leave the animals in peace. Please come back in a billion years, or something. I quite like that idea. There's also a friend of mine runs a project called WETI. SETI is the search for extraterrestrial intelligence. WETI is the wait for extraterrestrial intelligence. So Alex's point is that they're more advanced than us, we should just listen and wait for them to contact us. And there's an app that you can download that waits several billion times a second with no purpose whatsoever. But because the aliens will work out how to use the app to contact you if they want to. So it's a joke, but it sort of makes you think about exactly this point, which is that we're trying to do psychology as well, and I'm happy to talk about details later. Still got time for a few more questions if you want them. So,
why should the aliens be interested in us?
Yes, no, that's a very good question. Why should the aliens be interested in us? And I don't have a good answer for that, other than that we're interested in them. And so my assumption is, driven by ego, I think, is that I think that a technological society will be driven by science, and that involves exploring and understanding the universe around you. So I assume that any alien civilization capable of contacting us would be interested. Whether they're interested in talking to us is a different matter, but I think that they should be out there exploring. If they're doing that, I think we should be able to. It should just be blinding. If you have spacecraft that can travel through easily around the stars, I just think that should be obvious to us. And it's not, and so that's what worried me. And yes, I think you could explain it by saying they're hiding or that they're not interested in exploring. Actually, the most common variant of that these days is from people who like to talk about the forthcoming rise of computers and of artificial intelligence. And you can say, okay, well, the obvious endpoint for a civilization is that you eventually produce computers that have no interest in exploring and sit and consume the resources of a planet to keep themselves running. And again, that's in my possible but depressing bucket, because somehow I don't find that a very satisfying endgame for humanity. Yeah?
Do you think it would be a good idea if somebody wanted to produce a signal that would be picked up by another intelligent planet, to produce a signal that initially looked like a transient, so that people would find it, and then put in some anomalies that couldn't be explained, and then to be produced by the intelligent society?
Yeah, so the question is, should we be sending signals out, something that maybe looks like a transient and signals it? And not only do I think, well, I'm not sure whether we should, but people have done that.
I was sort of thinking back to the fact we have seen a transient that looks like a transient, it can't be a transient.
That's right, yeah, we do see transient things, but the question is how we can then convey its intelligence. So people often make an ego-driven assumption that mathematics or science is a universal language, and so people have done things like send signals that have a prime number of bits, and then a repeated prime, the idea being that there's no reason the universe should favour prime numbers, but if you're a mathematical society, you can. I have to tell you, it's probably a good point to end on, but let me finish by telling you about what we've set out into the cosmos. And I think, hopefully I mentioned on the way that we've only really explored a small bubble of space around our own star. And so really, I think our most powerful signals are those directed at individual stars, and they've mostly been sent by people trying to initiate this sort of very long distance, very slow communication. But there is if you ever go to the north of Norway, a beautiful town called Tromsø, which is freezing, a place to go and see the aurora. In the winter, I don't know what the locals do, but it's got 4 breweries. And I like Toronto a lot. But if you go just outside town, up on the hills, there's an enormous radar which belongs to an organisation called IceCat, which the UK is part of. And IceCat studies the Earth's upper atmosphere. They're interested in the northern lights and the aurora. And often they do things like send rockets up to create artificial aurora, or they'll pump energy into the Earth's upper atmosphere and try and excite it to see what happens. So IceCat's a wonderful thing. It's a unique station. But they ran out of money about 5 years ago. The various countries that funded it decided for a short period of time that they weren't going to fund the research. So the scientists, who don't like having their funding cut, decided to think creatively. And they realised they had the most powerful civilian radar in the world, and that they could therefore send the most powerful message ever beamed into outer space. And they targeted a nearby star, and they sold the content of the message to the highest bidder. And so, the highest bidder was Doritos. But for Doritos, carefully designed to look unmistakably intelligent, was beamed towards 3 of our nearest stars. And so if the aliens do come, at least we know what they're looking for. Thank you very much.